You know when you send an email or stream a video or just click a link on a website, have you ever stopped to think about how that actually works? I mean, how does your simple click travel across the world and back, like in the blink of an eye? It really does feel like magic. But it's not magic. It's actually a conversation.
And just think about the scale of that conversation for a second. We're talking billions of devices, phones, laptops, servers, you name it, all chattering away at the exact same time. You'd think it would be total, utter chaos, right? A massive jumble of digital noise. But it's not. It's orderly. So how does the internet pull off this massive global chat without everything falling apart?
Well, the answer is kind of funny, actually. It turns out our devices have learned good manners. Yep, just like us, they follow a really strict set of rules for communication. It's all to make sure that everyone is understood, nobody gets talked over, and every single message gets to where it needs to go.
In the tech world, this set of manners, this rule book, has a name. It's called a protocol. And you can think of it as the official grammar and etiquette for machines. It covers everything from how to say hello to how to say goodbye. Honestly, it's the secret ingredient that makes our entire digital world work. So, let's take a look at the rules, shall we?
Every single thing you do online, and I mean everything, relies on these protocols, and they all follow a few fundamental principles. We're going to break down the big ones: how messages get translated into a common language, how they're packaged up, the rules for their size and timing, and even the predictable patterns they follow. These are the building blocks that stop the internet from becoming a chaotic mess.
All right, so let's crack open this digital rule book. Once you get these principles, you'll basically understand the fundamental language of the internet itself.
Okay, first up, imagine you're trying to have a conversation with someone, but you only speak English and they only speak Mandarin. You're not going to get very far, are you? You need a shared language. Well, it is exactly the same for our devices.
For computers, that shared language is what we call message encoding. It's the process of taking your data, whether it's text, an image, or a video, and translating it into signals that can actually travel across the network. We're talking electrical pulses in a wire, flashes of light in a fiber optic cable, or radio waves through the air. Encoding is what turns your ideas into a language the network can understand.
All right, next rule, think about the last time you mailed a letter. You didn't just scribble on a piece of paper and toss it in the mailbox, right? Of course not. You put it in an envelope, you wrote a destination address, a return address, the whole shebang. Computers do pretty much the exact same thing.
And this process has a fancy name: encapsulation. Your data gets placed inside a digital packet. That's the envelope. And this packet gets a header. That's the address you write on the front. That header contains all the crucial info, like where it's coming from, and, more importantly, where it's going. It's what makes sure your data doesn't get lost in the mail.
Now, this next rule is one we can all probably relate to from our own lives. You know how in a group chat, it's kind of rude if one person just goes on and on in a giant wall of text? It just hogs the whole conversation? Well, networks feel the same way.
See, to keep things fair and fast for everyone, protocols have strict rules about message size. So a huge file, like a movie or streaming, doesn't get sent as one giant chunk. Instead, it gets broken up into thousands of tiny little pieces. This is amazing because it means you can stream your movie while someone else is on a video call, and neither of you lags. Plus, if one tiny piece gets lost, the network only has to resend that little bit, not the entire movie all over again.
A good conversation has a certain rhythm to it, a natural back and forth. You talk, then I listen. We try not to interrupt each other. And we don't talk so fast that the other person can't keep up. Well, computers have learned this lesson too.
Message timing is all about that rhythm and pace. You've got rules like flow control, which is basically one device telling another, hey, whoa, slow down, you're sending data way too fast for me to handle. Then there's response timeout. That's like if a computer sends a message and doesn't hear back after a certain amount of time, it knows something's wrong and it'll try again. It's the network's way of politely asking, you still there?
Think about how you answer the phone. It's almost always the same, right? You say hello, you have your chat, and then you say goodbye. It's a predictable pattern. It turns out a lot of digital interactions follow a similar script to make sure everything happens in the right order.
This is a perfect example of one of those patterns. Every time your computer joins a new Wi-Fi network, it needs a unique address, an IP address, to get online. So it has a little four-step conversation. First, your computer shouts out a discover message, basically asking, hey, is there a DHCP server out there? The server hears this and replies with an offer, saying, yep, I'm here, you can have this address. Your computer then sends a request saying, awesome, I'll take it. And finally, the server sends an acknowledgement, making it official. It's yours. Welcome aboard. All of this happens automatically in a split second.
Okay, so we've got the core rules down. Now let's put it all together and see how these rules guide a single message on its incredible journey from your keyboard out into the world. So let's follow the message. It starts with you, the message source. You hit send. Instantly, the encoder translates your message into signals. The transmitter shoots those signals out over the channel. That's the physical path, the wires, and airwaves of the internet. On the other side of the world, a receiver catches those signals, a decoder translates them back into data, and just like that, it arrives at the message destination. And every single step of that journey is managed by the protocols we've been talking about.
But hold on, the destination isn't always just one other person or one specific device. The rules also have to cover the delivery method. Is this a private one-on-one chat or more like a public announcement?
So this slide lays out the two main ways a message can be delivered. Over on the left, you've got unicast, which is a one-to-one delivery. And on the right, you see broadcast, a one-to-all kind of thing. Let's dig into each one real quick. Unicast is really the workhorse of the internet. When you click a link to watch a YouTube video, your computer sends a unicast request directly to that one YouTube server. It's a private, point-to-point conversation, just like sending an email to a single person. Honestly, almost everything you do online is just a series of these direct, unicast conversations. Broadcast, on the other hand, is the public announcement system. Here, a device sends out one message, and it goes to every single other device on the same local network. Remember that DHCP Discover message from earlier, when your computer was looking for an IP address? That was a broadcast. It was basically shouting into a crowded room, "Can anyone here help me?" It's super powerful, but you have to use it carefully so you don't create too much network noise. So, we've gone through the what and the how, but that leaves the biggest question of all, the why. Why does this invisible, super complex system of rules actually matter to any of us in our daily lives?
Well, it matters because this digital rulebook is, and this is no exaggeration, the foundation of our modern world. It's what lets us build global communities, it's what makes online learning possible, it's what enables us to work from anywhere. Every single tool we take for granted, instant messaging, social media, all of it, it only exists because these shared rules are in place, keeping the chaos at bay.
And that brings us to one last thought to leave you with. We designed all these rules for a world of humans talking to computers. But as we head into this new era of AI and smart devices all talking to each other, are the old rules going to be enough? What new manners, what new protocols will our machines need to learn to navigate the much more complicated conversations of the future?